we'll start be learning reaction number 6 today. So I thought we could learn 12, 14, but we're not out of time. We're in the important things. A lot of the others that I've kind of skipped over are sort of derivative of things we've already learned, so we're not going to worry too much about that. Okay, so let's see. We're just going to jump into it. Last time we had introduced mechanism type 3, and so it's a concerted mechanism, so we're going to form our carbon nucleophile bond at the same time as we form our carbon electrophile bond. And so we learned that the regiochemistry of this type of mechanism, it's still going to follow our Markovnikov type addition, but what we want to focus on is making sure that we have our nucleophile that has a slight partial negative on it aligned with our carbon that would have a slight partial positive charge on it, and vice versa. The electrophile needs to be closer to that carbon with the partial negative charge. So basically we want to make sure we're aligning our nucleophile and our electrophile correctly with our alkene. And then the stereochemistry, since we're forming our bonds at the same time, the stereochemistry is going to be set. Okay, so all right, so Sadie was on campus last week and had a few people taking pictures, so here are some of those pictures. She looks pretty absurd in these pictures, to be honest, but yeah, and she's pretty good. I told her to sit, and so she sat, and just let us take the picture, so good dog. All right, so reaction number 6, we're going to call hydroboration. Actually, it's not hydroboration reduction. I have written in my notes wrong. All right. So, with hydroboration, then we're going to hit that with a reductive workup step. So let's take a look at what that would be like. So we've got an alkene, we've got a double bond. So we saw last class why really this carbon will have a slight partial positive charge, and this carbon down here would have a slight partial negative charge, right? And it's because we do have other structures that are in equilibrium, and so a positive charge would be more stable on the tertiary carbon, so we give that the partial positive. So what we're going to do is we're going to align our BH2, or our BH3, in a way that makes sure that our charges match up. All right, so between boron and carbon, which is more electronegative? I'm sorry. Boron and hydrogen. Which one's more electronegative? You would think boron, but hydrogen is a weird beast. And so in reality, if you look at your Pauling scale, you're going to find that hydrogen has a value around 2.1, and boron has a value about 2.0. So which is really more electronegative? Hydrogen. And so what we've got is a slight bond dipole. It's going to put a partial negative charge on our hydrogen, and so vice versa, we'll end up with a partial positive charge on our boron. Okay, so have we lined up our alkene and our reactant correctly? Yeah, absolutely. So how are we going to start our mechanism? How do we start every mechanism? Arrow from the electrons, and specifically an arrow from the electrons of the pi bond. And so which do you think we're going to attack with that arrow? Is it going to be the hydrogen or the boron? It's going to be the boron, right? Because electrons are going to be more attracted to an atom with a partial positive charge, and so we show that. And so at the same time, we learned last class that in a concerted mechanism, our nucleophile, which is in this case is the hydrogen, is going to add at the same time. So we start our arrow with that BH bond, and we snap it back to that tertiary carbon. All right, so 2 arrows in this case. So what we end up with is this going to be a syn or an anti-addition? It has to be syn, right? Because it's a concerted mechanism. We're adding things at the same time, and so we have to be adding them to the same face. All right, so what we'll have is if we add from the front face, where will we show the methyl? This methyl right here. It's going to be pushed back, right? So that's going to be on a wedge, or I'm sorry, on a dash. And so the hydrogen has come in and is now on a wedge. And so likewise, the bromine has come in from the same face, and so we've got BH2 connected at that position. Okay, so this is an example of a syn addition And so furthermore, we can attack from the back face. Now instead of having to draw out those structures and say that we've got this plus the other structure, what could we just simply say? Yeah, we've got this structure plus we've got an enantiomer. All right, so that would be perfectly fine. I have so many things in my head. All right, so we've got plus an enantiomer. All right, and so I think this is our first example of where we had to do a workup step. And so the problem is we've got this molecule with a boron connected to it, but when I showed you those pharmaceuticals on the problem set, all those different drugs, how many of them had a boron sticking off of them? None of them. It's not very synthetically useful to attach a boron. At least in Chem 206, it's not very synthetically useful. And so despite the fact that we have this boron and it's stable, we need to get rid of it. So what we found is we have a stable intermediate. So what we're going to have to do is we're going to have to undergo what we call an oxidative workup. All right, so it's going to be an oxidative work. I keep saying oxidative. It's a reductive workup. Give me just a sec. Let's get down to the bottom of this officially. This is going to be, I was right the first time, it's an oxidative workup. I'm very sorry. All right, let's go back to our title, oxidative. What a mess. All right, so oxidative workup. And we know it's going to be an oxidative workup because the things we're treating it with include hydrogen peroxide, which is a strong oxidizing agent, along with sodium hydroxide. Okay, so here's the key thing about the workup step. We don't care about the mechanism. Yeah, there's something mechanistically going on, but we're only going to worry about this first step because this is where we set our stereochemistry and our regiochemistry. In a lot of cases, what we find is the workups can end up being a little more complicated than really we could get a handle on in Chem 206. So we're not going to worry about the mechanism. What ends up happening is essentially our stable intermediate. We don't do any chemistry at the top carbon, but what happens is we cleave off our BH2, and that gets converted to an OH. And so importantly, we show the BH2 here on a wedge. We're also showing the OH on a wedge, and so we are going to retain our stereochemistry when we convert it from the BH2 to the OH. So let's make sure we write that down. Of course, we also have plus an enantiomer. And so importantly, we will retain stereochemistry when converting BH2 to an OH. Yeah?
Is the other wedge that's sticking out the thing, is that the hydrogen?
Mm-hmm.
Okay.
Yep. All right, so we didn't do chemistry there, so we've got the same exact stuff there on the top carbon. Okay, so that's useful, because if we've seen alcohols in any pharmaceutical products, yeah, they're all over the place. And so importantly, we've learned how to make an alcohol before, right? So we've learned that we can do this. So, for example, if we had a starting material that looks like this, we know that we could treat it with H2O and catalytic acid, or we could treat it with mercury acetate, followed by a reductive workup of sodium borohydride. And so in each case, what we'd end up with is a product that looks like this. So we would have that product, right? And so when we talk about the regiochemistry of this, all right, both of those reactions undergo what kind of regioselectivity when we add our hydroxyl group? It's Markovnikov, right? We're adding our OH group to the tertiary carbon in both cases. So what we've got is a Markovnikov addition. But as you might expect, there could be cases that come down along the lines where we want to convert an alkene to a hydroxyl group and actually have the other regiochemistry, right? So add to the less substituted carbon. And so following what we've done above with our hydroboration oxidation, all right, so we can see we've got a secondary carbon here and a tertiary carbon there. And so we end up with our hydroxyl group on the secondary carbon, right? And so if we followed a Markovnikov addition, no, right? If we were undergoing a Markovnikov addition, we will have added our OH group to the tertiary carbon, but that's not what we see. And so now we've got different strategies. If we go the other way, we could undergo a reaction with BH3 followed by our oxidative workup of H2O2 and sodium hydroxide. And so the product we would have in that case would be this, where instead of adding it to the tertiary carbon, we've added it to the primary carbon. And so this is part of synthetic chemistry. What you get into is you'll find that, yeah, sure, you can throw a hydroxyl group onto that double bond, but you can't always get the product that you're hoping to achieve because each reaction you do is going to have characteristic regioselectivity or stereoselectivity. And so part of the challenge is thinking about not only adding your necessary functionality, but adding it in the correct way. Yeah.
So the reason that the functional group gets added to like the primary carbon instead of the tertiary is because of the difference, like because H is more electronegative than E.
Yeah, exactly.
So it just depends on like what compound you're using.
Yep. And so in this case, we take advantage of the fact that hydrogen is more electronegative to add in now some more substituted carbon, which gives us this intermediate, which we can cleave off, form an OH group. And ultimately, in 2 steps, we've done the opposite of this right here. Instead of adding the OH to the tertiary, we've added it to the primary. Yeah. All right, so really, really, really useful. I'll say this. What do you think the odds are in an exam that I would maybe show you a starting material, show you a product, and then ask you what would be the correct way to add that alcohol? It's pretty likely. So keep in mind that we've ultimately got 2 different strategies in terms of adding an alcohol. We can add it in a Markovnikov fashion, or we can now add it in what we call an anti-Markovnikov fashion. Okay, so let's add that to our table. This should be reaction number 6. And so unlike our catalyzed water addition or our oxymercuration, now what we end up is our electrophile is what? Yeah, in this case, instead of adding the hydrogen as our electrophile, we're actually adding water as our electrophile. That's how we get the different regioselectivity. And so our nucleophile that we end up with on our product is going to be hydrogen. All right, so what you'll see as actual reagents is you can treat this with BH3, or you'll see B2H6. And so that can be a little confusing. Don't even worry about it. Just treat this. So let's draw it down here. Treat B2H6 pretty much as BH3. Just pretend you've got BH3. But in reality, you'll see, I think one of the homework problems uses B2H6, so I don't want you to be confused by that. All right, so of course it's a 2-step reaction. We've then got to hit it with hydrogen peroxide and sodium hydroxide. All right, so BH3, how stable do you think BH3 really is by itself? Is it open shell or closed shell? It's open shell, and so maybe unsurprisingly, you can't go to the chemical store and just buy BH3. What you're going to have to buy is BH3 basically forming what we call an adduct with another molecule, and so it's commonly found, purchased as what you'll see written as BH3 with a dot with THF. And so what THF is, it is a solvent, a commonly used solvent that looks like that. And so what's happening is once you take your BH3 and you add it to your THF, well, does THF have any lone pairs that would probably be happy to donate in and close the shell of the BH3? Yeah, absolutely, right? And so really what you've got when you have BH3 THF is you've got a structure that looks like that. So if you ever are in need of buying BH3, that's probably how you're going to find it. You're going to find it mixed with another solvent so that the shell is closed. All right, so the regioselectivity. Markovnikov? No, it's anti-Markovnikov, and it's the only case that we'll see of an anti-Markovnikov addition. What about stereoselectivity? It's syn, right? And so we know that it's syn because we're going through a concerted mechanism. So all concerted mechanisms are going to have to go through this syn. Okay, so let's forge forward and we'll start reaction number 7. And so this one doesn't have a nice and neat name, I guess. And so what it is we'll start with a given material. We're going to treat with osmium tetroxide. We'll draw out osmium tetroxide to see what that looks like. You might see at some point in your careers KMNO4. It does the same thing, but I'm going to focus just on the osmium tetroxide in this class. So just a heads up, sometimes you can see the KMNO4. And again, we're going to have an oxidative workup because we're going to find ourselves with a stable intermediate. In this case, the oxidative workup is pretty easy to remember. It's just water. So we run this reactor, we run this first step without any water, and then basically we add water to it for the second step, and we end up with the product that we want. All right, so it's a concerted mechanism, which means do you think it's going to be syn or anti? It's going to be syn. And so if we add the stuff to the front face, we know that's going to push our methyl group back to be on a dash. And so I guess what is the stuff that we're adding? So in this case, we're going to have two things on a wedge. And so to that tertiary carbon, we're going to add an OH. And then to the secondary carbon, we're also going to add an OH. And so what we end up doing is we're going to add 2 hydroxyl groups now to our double bond. And so we call that a diol because there are 2 alcohols, right? And so we have our diol formation. Of course, we would form this product plus what? Plus the enantiomer, because we can always add from the back face as well instead of the front face. All right, so mechanistically, how does this thing work? So I'm going to use, let's see. We'll just show the same starting material. So what does osmium tetroxide look like? All right, so we have osmium. So basically what it is it's osmium double bonded to 4 different oxygens. So it's going to look like that. Now osmium is on the periodic table down at atom 76, and so it's not limited by the octet rule. There's a lot of different orbitals going in osmium. So it can violate the octet rule, and that's perfectly fine. Metals do weird things. All right, so where are we going to start our arrow, do you think, in this case? As always, we're going to start our arrow with the electrons of the alkene. And so what we're going to do is we're going to draw our arrow to one of the oxygens. So this mechanism ends up looking a little funkier than anything we've seen before. And so our red arrow here is going to be forming a new bond between a carbon and an oxygen. And so what about this oxygen? Would we be violating the octet rule in that case? Yeah, so if we added another bond to our oxygen, we'd have 5 areas of electron density, and so that's no good. So what we've got to do is we're going to have to break the pi bond, and we'll show that going back to form just a lone pair on our osmium. All right, so all along, we know this is a concerted mechanism, and so we need to be forming a second bond. Well, as we form this lone pair, we're going to be having a charge build up on that osmium. So what we want to do is then remove electrons from the osmium, and we show that by basically taking the top pi bond and forming a new bond between the oxygen and the carbon right here. And so what it is that these 2 arrows, the long arrows, the bottom one and the top one, they're just new carbon-oxygen bonds being formed, and then the third small arrow we're going to make a lone pair. So this will be a little more clear once we actually show what our stable intermediate looks like. So we're going to add from the same face. So we'll have an oxygen there on a wedge and an oxygen here on a wedge. And ultimately what we end up with is a new 5-membered ring that looks like that. All right, so that's all we need to know mechanistically about this reaction. Of course, as always, we've got plus an enantiomer that could be forming. Of course, when we looked at the drugs on the problem set, none of them had an osmium connected to them, and furthermore, osmium is fairly toxic, so we want to get rid of the osmium, and so by doing a workup step of just water, we don't worry about the mechanism, you're not responsible for it, essentially what happens is we're going to cleave off our osmium, and we end up with the diols in question. All right, so we have OH here and OH here, plus an and. So you're just responsible for the first step. You don't have to worry about any of the workup step afterwards. All right, so let's add that to our table. So let's see, this is reaction 7. So what's our electrophile end up as? It's just an OH, and so the same for our nucleophile. We're adding the same thing to our double bond to each side. All right, so we have a couple of OHs, and so the reagents we'll use, we always want to hit it with osmium tetroxide, and then followed by a water workup. Do we have any regioselectivity since we're adding the same thing to both carbons? No, we don't have any regioselectivity in this case, so we just say none. We don't have to worry about it. What about the stereoselectivity? It's definitely syn, and we know it's definitely syn because we're going through a concerted mechanism. So basically, we're forming our new carbon-oxygen bonds at the same time over here in this first step. And so that sets our stereochemistry, and whatever product results, it will keep that stereochemistry as we go. Okay, so I wanted to take a little bit of a timeout. We've been doing a lot of cyclic examples as we've gone, and so what I wanted to do is maybe look at some acyclic examples and think about the sorts of things that we might see on an exam. So, it's perfectly fair for me to ask you a question like this. So, instead of asking you to predict the product, I can ask you to predict the starting material. And so we're going to learn a really important lesson basically by going through this exercise. So let's say that we end up with a product that looks like this. So I ask you, all right, so how could we have some starting material that goes in our question mark that would lead to this product? Now, have we learned some way that we can form a diol? Yeah, absolutely, we just did. So we know that the reaction here is going to be with osmium tetroxide and then with water. And so importantly, we just said that whenever we do this reaction, we're going to have syn stereochemistry every time. All right, so anytime we form diols using osmium tetroxide, we're going to end up with the syn products. So let's think about what we're going to do is we want to keep track of our stereoisomers. And so for carbon number 1, we would say that that's higher priority. Then we've got 2, 3, and 4. And so is that going to be R or S? Our thumb coming out towards us on the hydrogen. Could we curl 1, 2, 3 with the left hand? Yeah, definitely. So this stereocenter will be an S. And so the stereocenter on the right, we've got 1, 2, 3, 4. And so, all right, again, our hydrogen's coming towards us. And so can we curl, let's see. I made 2 1s. I can't. All right. So we've got, again, with our left hand, can we curl 1, 2, 3? Yeah, absolutely. And so what we've got is we've got a couple of S stereocenters. And so let's think about what this thing really looks like. So to maybe make it a little easier, what I'm going to do is I'm going to draw a Newman projection. It's basically looking from our green eyeball here. So let's say that the Newman projection we're drawing is for this structure. So we'll have a hydroxyl group straight up. We're going to have a methyl group to the bottom left. A hydrogen to the bottom right. All right, so then for the hydroxyl group on the back, it is straight down in the plane. We have an H to the top right, and a methyl to the top left. Now, we know, what 2 things are we adding to this molecule? The OH groups, right? And so that's what we want to focus our attention on. We want to focus our attention on the OH groups. Now, we know that this addition must be a syn addition. And we know it's a syn addition. Why? Yeah, it's a concerted mechanism. That tells tells us that it has to be a syn addition. So as I've outlined this molecule, would you consider these two OH groups to be syn or anti? They're anti. And so what we need to do is basically align them so that they are syn, so that we can compare how the other substituents will line up. So how can we do that? Yeah, we've got a CC bond here that we can freely rotate. And so if we hold the carbon on the left in place, and we rotate the carbon on the right 180 degrees, let's say we'll do a 180 degree bond rotation. What we'll end up with is a structure. All right, so the left side will be the same. Are we changing the stereochemistry at all? This seems to be a little bit of a misconception that I'm getting. So when we do a bond rotation, we're not changing the stereochemistry. The relative orientation of our substituent stays the same. All right, so we're still gonna have an S stereocenter on the left, and we're still gonna have an S stereocenter on the right. Okay, so let's see. We want to flip our carbon on the right 180 degrees. So that's going to put our hydroxyl group still in the plane, but now oriented up. So that means we'll have a dash down and a wedge down. And so what's going to end up on a wedge? Is it going to be a methyl or a hydrogen? Yeah, and so let's think about it. So let's focus in on this methyl right here. And so as it's oriented, it's going up. And it's also on a dash, right? So if I orient my laser pointer this end, it's going to look like this. What's going to be 180 degrees to the front end? Yeah, it's going to be on a wedge now, right? And so if it's pointed up, basically if it's pointed up on a dash, if we rotate 180 degrees, it's now going to be pointed down and on a wedge. So our methyl group that was on a dash will now be on a wedge, and vice versa. Our hydrogen that was on a wedge will now be on a dash. And so we can see that if we draw another Newman. All right, so we're going to keep the front carbon in place, and ultimately what we'll do is we will rotate the back carbon. All right, so now are we going to end up with an eclipsed or a staggered conformation? It should be eclipsed, right? Because if this is our eyeball, we shouldn't be able to see this second hydroxyl group. So we've got an eclipsed conformation. We've got our methyl going down to the right, and we've got an H going to the left. Okay, so now, have we oriented our hydroxyl groups in what you would call a syn orientation? Yeah, absolutely. So now we've got our hydroxyl groups in an orientation that we could call syn. Over here, since they're on opposite sides, we would consider that anti. And so from there, it's pretty straightforward. All right, so what we want to do is we want to group our substituents together. And so we can see that this hydrogen and this methyl are on the same side, right? They're basically eclipsing each other. So we'll box those in as red. And so likewise, a hydrogen and a methyl on the right side, we'll box those in as blue. And so when we draw the starting material for this reaction, all right, so basically you can imagine instead of adding the OHs, let's just pluck them right off. And so what we're going to have is these two groups will stay together on one side of the alkene, and these two groups will stay together on the other side. So our starting material, all right, so we would have on carbon 1, a methyl on one side, so we'll draw that in red. And so on the same side of that new alkene, we see that we've got on the back carbon a hydrogen. And so that's what we show on the alkene. And so vice versa, on the other side of our alkene, we know on the front carbon we've got a hydrogen. So we'll show that in blue. And then on the back carbon, what have we got? That's the methyl, right? All right, so let's think about what this tells us. What it means is that if we want to be able to form the product that is the SS stereoisomer, what we're going to have to do is this double bond, is it E or Z? It is definitely E, right? They are enemies. They're going to be on different sides. And so what we have is that the E stereoisomer of our double bond is going to be able to provide the SS stereoisomer. So do you think the Z stereoisomer would be able to provide SS? I'll go ahead and tell you it won't. And so that leads me to my point of this entire section. What we want to keep in mind is that the stereochemistry of the product depends on the stereochemistry of the alkene. All right, so we can prove that. What we can do is basically the same process. Instead of using the product I've shown above, we can try it with the Z alkene. So let's see what we get if we use the Z alkene instead of the E alkene. All right, so we're going to use Z, and we're going to see what product we get to. So the Z would look like this. We would have, and so I'll orient it basically. I'm going to put it in the, I'm going to flip it 90 degrees from the plane of the paper. So we'll put a hydrogen on a dash. On the left side, we'll put a hydrogen on a dash, which puts a methyl on a wedge. And on this side, a methyl on a wedge. Are we all in agreement that this is going to be the Z stereoisomer? Yeah, definitely. So we've got the methyls on the same side. So we've swapped our methyl groups. We've now got the other possible stereoisomer for 2-butene. So let's do the same reaction. All right, so we want to make sure that we're following the same reaction. So we've got osmium tetroxide followed by water. And we know that it has to be a syn addition based off that mechanism. So we've got two possibilities. We can basically either add our diols to the top face of our alkene, or we can add our diols to the bottom face. So let's see what we get. All right, so if we add to the top face, we'll show our carbons oriented together, and then we'll show the hydroxyl groups both in the plane on the same side. And so have we added our hydroxyl groups syn? Yeah, we've absolutely added them syn. We've added them from the top side. And so what that means is that, all right, so let's focus on this left carbon. We've got a methyl on a wedge, and we've got a new hydroxyl group coming in that's basically going to push these two substituents, the hydrogen and the methyl, it's just going to push them down. Are they going to stay each on the wedge and the dash that they were on? Yep. Yeah, absolutely. They're going to keep their relative orientation. And so the hydrogen that was on a dash, it's still on a dash. It's just going to kind of be pushed down now, right? Because we're changing the hybridization of our carbon from sp2 to sp3, and so we're going to take a different geometry. And so the methyl that was on a wedge, it remains on a wedge. It just gets shoved down a little bit by our incoming hydroxyl group. So the same thing will happen on the right side. We had a hydrogen on a dash, and so it will remain on a dash. And then we've got a methyl group on a wedge, and so there it is, perfectly happy on a wedge. All right, so let's think about what stereoisomer we have here. We've got 1, 2, 3, 4. So is that going to be R or S? All right, so if we align our right thumb going back with the hydrogen, can we curl 1, 2, 3? Yep, definitely. So we've got R on the left side. And then what about on the right side? We've got 1, 2, 3, 4. And so let's see, we align our left hand back and we curl 1, 2, 3. Yeah, so we can do that with our left hand. So we've got the S stereoisomer here. And so what we're finding is that while the E stereoisomer is going to lead to the SS product, or if it attacked for the other face, it could have led to the RR product, the Z double bond is going to lead to the RS stereoisomer. And so we end up getting different products here. We get different stereoisomers based on which starting alkene we had, either the E or the Z. Of course, we could have two products, right? Because we could have not only attacked from the top face, we could also have attacked from the bottom face. And so we'll go through a similar exercise. So now we'll have our OH groups having added syn on the bottom face. And so we'll keep our relative orientation. So these things, instead of being pushed down, they're going to be pushed up. And so the methyl will still be on a wedge, but now we're pointed up. And so we do that to both sides of the molecule, but we get a product that looks like that. Okay, so what's the relationship between these two things? Yeah, I heard meso, and so that's exactly correct. These things are actually meso. So if we look for the stereocenters, what we would find is now we should have the S on that side and the R on that side. So do we have a plane of symmetry? Yeah, what about the plane of the board itself? Yeah, so we should. And so let's think about it this way. So if you took this molecule basically, and so my thumb, it would be on a wedge, right? Just like the methyl group. What we're going to do is we're going to flip the molecule over 180 degrees. Basically, imagine it's a car and we're just going to put it on its roof. And so when we do so, that methyl group that I've got right here, would it still be on a wedge? Yeah, definitely. So that's what we've got there. And so in fact, what we would find is we've got exact mirror images of each other. These are not enantiomers because they are in fact the same molecule. It's just they're flipped over from each other 180 degrees. All right, so if you don't believe me, what you could do is you could take this molecule, you could basically try to find its mirror image, and what you would find is it, again, is just going to be the same exact molecule. So what we've got is we do have a plane of symmetry. In this case, it's the plane of the board. And then do we have a 1-to-1 ratio of R to S? Yeah, we do. And so in this case, if we start with the E double bond, we would end up with a pair of enantiomers, the SS and the RR. If we started with the Z double bond, we would end up with just one product, and in this case, it would be the meso product. Would the E stereoisomer lead to an optically active product?
Yeah.
It would, right? Because SS has an enantiomer, it's RR. Would the Z double bond lead to an optically active product? No, and that's because since RS is meso, we know it's achiral, and if we have a molecule that's achiral, it's definitely not optically active. Optically active molecules must have an enantiomer. Okay. Let's do another one. Really quick. All right, so in this case, let's say we've got some mystery molecule. So our mystery molecule is going to produce this product. All right, so we'll put a methyl on a wedge, hydrogen on a dash, methyl, and hydrogen. Okay. So do we know some way that we can basically add 2 chlorines to an alkane? Yeah, so what we learned, I don't remember which number it was, but we can undergo a halogenation, right? We can basically react our alkene with Cl2. And so importantly, what kind of mechanism would that reaction go through? Carbocation? Or halonium? It's a halonium, right? We end up with a 3-membered ring with a positive charge on chlorine. And so importantly, the stereochemistry of a halonium-type mechanism, is it syn or anti? It's anti, right? And so what we want to do is basically make sure that we align the 2 things that we've added, in this case the 2 chlorines, in an anti-fashion. Now, as it's drawn, are they syn or anti? Yeah, they're currently syn. And so what we'll do is another bond rotation. So we'll keep the first carbon in place. But now we'll have the chlorine straight down. And so what will be on a dash? Is it going to be the methyl or the hydrogen? It should be the methyl, right? Because if we've got the methyl on a wedge coming towards you, well, 180 degrees from where I'm pointing is going to be up and on a dash. And so that's exactly where the methyl goes. And so we end up with that. So now do we have our chlorines aligned to anti? Yeah, absolutely. So now they're on opposite sides of each other. And then basically we're just going to go through the same exact exercises we did above. So what we want to do is imagine, you can imagine we're looking down this bond. And so we want to think about the things that are on our right side, and we want to think about the things that are on our left side. And so we can see that our methyl group and a hydrogen would both be on our right side, right? They're both on wedges, and so if I'm looking, I guess, this direction, both of those are going to be coming out towards you, so both on my right side. So they'll be together on one side of the double bond. And then likewise, the things on dashes will be together. So when we draw our starting material in this case, we're going to have an alkene that looks like this. And so on one side together, it doesn't matter which, you can just pick one. We'll make this the red side. On the first carbon, we've got a methyl. On the second carbon, what have we got? Yeah, we've got a hydrogen. And so likewise on our left side, we've got a hydrogen on the front carbon, and we've got a methyl on the back carbon. So what we've said already is that the ultimate stereochemistry of our product is dependent on the stereochemistry of our starting material. So if I asked you on an exam, all right, if you started with 2-butene, would you have to start with E2-butene or Z2-butane to end up making this product? What would you say? Yeah, we've got to start with this exact stereoisomer of 2-butene, right? And so is this E or Z? This is definitely the E stereoisomer. Okay, so key important point. And like I said, we've been doing a lot of cyclic examples, and so I wanted to have some acyclic examples down because we can see that the bond rotation can kind of make it a little more complicated. We don't see that bond rotation in cycloalkanes. Okay, so that's the end of our time now. Reaction 8. This is a pretty cool one. This one is unique. All right, so this is ozonolysis, and so literally, it is what it sounds like. It's the reaction of an alkene with ozone. And so any good synthetic chemistry lab has what we call the ozonator, and so these things can typically be pretty bulky, and so you keep it in a closet, so you need some ozone. But ozone is pretty toxic. It's a gas, so you don't just have ozone sitting around. And so what you do is you wheel your big green box into your hood and you turn it on and it's really loud. And basically it makes ozone from oxygen in the air. And so you just pipe a tube into your reaction and the ozone will flow into your reaction flask and you can treat your alkene with ozone. And some of the reactions we've learned are, they're not heavily used in real synthetic chemistry, but I will say that ozonolysis is very heavily used. It's actually a really, really useful change that we can affect the molecule with. So let's just look and see what happens. All right, so we'll start with the starting material, and we'll just draw this symmetric alkene, and we'll call this carbon 1, and we'll call that carbon 2. All right, so we're just basically looking at the two carbons that are connected together. And so what we'll do is, again, this is going to be another two-stepper, so we're going to end up with a stable intermediate. So the first thing we do is we hit it with ozone. All right, so we react it with O3. And then the second step, we're going to do a workup, but there's actually going to be two possibilities. All right, so we're going to have two different types of workup that are going to lead to two different types of products. And so that even further increases the synthetic usefulness of this thing. We now have multiple products that we can form based on which workup we choose. But we'll worry about the workups in a few minutes. And so the thing to remember, anytime you see ozonolysis, is that it is all about cleavage. So it's all about cleavage because that's literally what we're going to do. We're going to go up to our molecule, our double bond, and we're just going to cut it in half. All right, so to draw first off, how many products are we going to form? Yeah, we would expect to form two. In this case, because of the symmetry, they'll end up being the same thing. But yeah, since we're going to cut this molecule in half, we are going to end up with two possible products that we could form. So to think about what those would be, let's just draw the top half. And so interestingly enough, we're going to keep that double bond. All right, so that's number 1. And so this is number 2. The only difference is that what we find that carbon is double bonded to is no longer a carbon, it's now an oxygen. And so essentially what we're able to do is we're able to take two carbons that are double bonded together, and we're able to cleave this thing in half, and we end up with two new products. In this case, they're the same thing just because of the symmetry, but we end up with two possible products where now our carbons, instead of being double bonded to the other carbon, it's now double bonded to an oxygen in that place. Okay, so let's see. I don't think we're going to be able to finish this one. Let's do the two possible workups, I think, and then call it a day. So, like I said, we're going to be able to do two possible workups for this reaction. And so let's see how those things really differ. So we'll start with the starting material. We'll put a methyl on one side with a hydrogen, and then on the other side, we'll just put a couple of hydrogens. And so we hit it with ozone. And so the first thing we'll show is we're going to do what we call a reductive workup. And so what we treat our mixture with is going to be dimethyl sulfide. So it's just a sulfur with 2 methyl groups connected to it. And so we call that a reductive workup. And so what do we do? All right, so we know that it's all about cleavage, so we're going to cut this thing in half. And so let's say that this is side 1, and this is side 2. So over here we'll show our side 1 product along with our side 2 product. And so we copy everything over, except now we change it to a CO double bond. And that's pretty much it for the reductive workup. Importantly, nothing really changes, all right? So that's basically flat out, we're just going to convert the CC double bond into a CO double bond. So then for the side 2, we end up with this molecule. Have we made 2 different products? Yeah, definitely we have 2 different products in this case from our starting alkene. Okay, so that is a reductive workup, and so let's just say the reductive workup, nothing really changes from what we learned already. Nothing changes except for our cleavage. All right, so then the other, if we've got one that's a reductive workup, what do you think the other is? It's an oxidative workup. And so for the oxidative workup, we're going to hit that with hydrogen peroxide. I think it's just hydrogen peroxide, and that's fine, not too important. And so this will be our oxidative workup. So an easy way to remember it is that, well, it's oxidative. We would expect it to have oxygen. A lot of oxidizing agents do, and you can see hydrogen peroxide does have an oxygen. So very, very common oxidizing reagent. And so what we end up with is we're going to have very similar looking products. However, anytime, and it's important to say this, anytime that we have a hydrogen connected to the alkene itself, that hydrogen is going to be swapped out for an OH group. All right, so would these hydrogens count? No, they're connected to this, they're part of this methyl group, and so they're not directly connected to the alkene. But what about this hydrogen on the right? Yeah, absolutely. It's connected to our top carbon, and so what we see is it is now converted to an OH group. And that's pretty much the single difference between these 2 workups. So the reductive workup keeps it the same. The oxidative workup is going to switch it to an OH group. All right, so will we see a different side 2 product in this case? Yeah, definitely. What we'll end up with, in reality, this would be a really unstable molecule, but for Chem 206, we'll say that it's perfectly fine. And so in both cases, we've got 2 hydrogens. In the second case, we've got 2 hydrogens connected to this carbon of the alkene, and so we end up with 2 OH groups here. And so importantly, we want to add that anytime we do an oxidative workup, we just say that H's connected directly to alkene become OHs. All right, so why that's really synthetically useful is here we formed an aldehyde. Down here, what would we call this functional group where we've got a CO double bond and then an OH off of it? It's a carboxylic acid, and so now what we can do is we can use basically ozone to form either of these functional groups based off of which workup. All right, we've got the workshop this evening from 4 to 6.